Now we're going to start on the last unit, on the last chapter of this course. And I think this is one of the most important topics that you can learn as an engineer and as an engineering scientist, engineering researcher. And it's on the topic of differential equations in general. We will start with ordinary differential equations. If we have time, we might touch on partial differential equations. You are not responsible for partial differential equations, but you'll get to learn them at some point in our program, how to solve them numerically, but at least we will cover ordinary differential equations. I know some of you are taking ODEs or have taken ODEs, so can I see some hands, like if you've taken or currently taking ODEs? Okay. Again, you're probably taking it in a math school, right, or a math course, right? And you're proving lemmas and theorems and things like that. Sometimes you solve ODEs that look like dy by dt equal x cubed. Like, what the heck does that mean, right? And it's hard to see the meaning beyond that, but those are still important courses to take. I hope in these lectures, in this course, that I will give you a little bit more context and meaning to assign to those ODEs that you see and learn in your math courses, so that you have a slightly different physical insight into what those ODEs mean. Okay. The learning objectives for this unit are: first, you're going to learn how to define a differential equation, whether ordinary or partial or extraordinary. We'll learn why we call it ordinary and why we call the other one partial. Define and identify dependent and independent variables, coefficients, and the right-hand side of a differential equation. That's the nomenclature we will be using, at least from the perspective of engineering and numerical methods. Distinguish between a PDE and ODE, partial and ordinary. Identify and classify ODEs, initial and boundary value problems. We will call those IVP for initial value problem and BVP for boundary value problem. Describe the meaning of terms in an ODE. So a source term, for example, an input term, an input source term, or a sink term. And for spatial ordinary differential equations, you have diffusion and advection and reaction. So we'll learn what those mean. Order reduction for high order initial value problems. So for initial value problems, we have a generic way of solving them numerically, and that is to convert any second order and higher initial value problem into a system of first order initial value problems. Makes the solution much more general, and pretty much all codes out there like MATLAB and Python provide methods to solve systems of first order ODEs. Then you say, well, how can I solve a second or third order ODE? Then you convert it into a system of first order ODEs and you solve that system. Okay? Create Python code to solve a single or a system of ODEs using odeint, which is the built-in integrator in Python. Just like we did throughout the course, we're going to learn a built-in method so that we learn how to drive and have a win, right? And then we'll open up the hood and see what goes on under those methods. Okay, so we will learn to write our own codes as well, using our own routines, and as well as odeint. We'll use explicit and implicit. So once we go under the hood, we're going to learn explicit and implicit finite difference methods to calculate a numerical solution for an initial value problem, single equation or system of equations. For boundary value problems, we will use the finite difference method to calculate a numerical solution. We kind of did that already with the heat transfer problem. So the emphasis in these lectures is going to be on initial value problems. We'll probably dedicate just half a lecture or one lecture on boundary value problems, because we already did those with the heat transfer problem. And then identify when the right-hand side of an ODE is nonlinear and when to use a nonlinear solver. So we're going to circle back to nonlinear solvers. Okay. And finally, calculate a numerical solution for an implicit method with a nonlinear right-hand side using Newton's method. Okay, so what is a differential equation? We're going to do some lightweight activities today. So what is a differential equation? Not ordinary, not extraordinary, just differential equation. Yeah, you can talk to me, whatever. It's a small class today, so we can all talk together. rates of change. So an equation that has rates of change in it. Yeah. What do you think? Yeah. Yep. Yep. Which are rates of change. So you're right. Any equation that has a derivative in it, partial or total, that's a differential equation. Okay. So more formally, a differential equation is an equation with terms that involve the derivatives or rate of change of an unknown quantity. Okay. So for example, here is a differential equation. This is an advection diffusion equation. We'll learn more about those terms as we learn about differential equations. The dependent variable is the variable that is always being differentiated. Okay, so in this case, it's T, or temperature, for this problem. The independent variable is the variable that is in the with which we are differentiating the dependent variable with respect to. That sounded weird, but it's the variable in the denominator of the derivatives. Okay, this case x, which designates space, and these guys here, k and u, are the coefficients in a differential equation. They can be constant, they can be a function of the independent variable and or the dependent variable. So k and u could be a function of the temperature, could be a function of space. So for example, k is what we know as the heat diffusion coefficient, which we saw in the heat transfer problem. And that k usually tells you how fast heat is being transferred throughout the material. Now that k could be dependent on location. So let's say you're looking at heat transfer through an insulated wall, right? So you have the drywall first, that has one coefficient of heat transfer, and then you have some insulation which has a lower rate of heat transfer because it's an insulation. Then you have drywall, then you have air, right? So you could have a spatially changing heat transfer coefficient. So that is going to depend on x in this case, on location, right? But that thermal transfer coefficient, heat transfer coefficient, also depends on temperature usually. Okay, the more heat there is, the lower the heat transfer coefficient, or the higher, depending on the material. Okay, so you could have those cases as well. All right. So now the question is, why on earth do we develop equations with rates of change in them? And this is where I'm going to take you on a detour, on a significant detour. Don't get lost. Okay, don't get lost in the forest. We're gonna go through some weeds. We're gonna go around and circle back to differential equations, because I want you to have an intuitive understanding of why we do differential equations in the first place. Why can't we just find a formula for something? Okay, and I'll give you a reason first, and then I'll prove to you why it's easy, why that reason is valid. We develop equations with rates of change in them because you will see as you grow in your career, it is often much easier to describe physical laws and complex systems by finding relations between rates of change rather than just developing formulas for something. Okay, if I tell you develop the formula for the change in temperature in the wall, you're like, I have no idea how to do that. But it's much easier to develop an equation for the rate of change of that temperature, because we understand the rates of change of heat, and then solve that equation to get the formula for the temperature. Okay, so let's do an example, and this is where I'm going to take you on a detour. We're going to talk about lobsters a lot in this lecture, okay, or eggplants if you are a vegetarian. And we're going to talk about population growth, and one of your colleagues mentioned the carrying capacity of a population at some point, so we're going to hit that head on. But this is not a course on population growth, okay? This is not a lecture on population growth, so don't take this as an example to motivate you for the study of ODEs. It's a simple example that is that sets the ideas in your brain really well, okay? So this is not a course or a lecture on population growth, all right? So here's a motivating example for using differential equations. The paramecium is a unicellular organism that divides after a certain number of days. So this is a prime example of cellular division. So each paramecia, or each paramecium divides into two after a certain number of days. So in this population, the individuals divide once per day. So every day they double. So if you have one paramecium, then on day 2 it's going to be 2, on day 3 is going to be 4, and so on. Okay, And so starting with a single individual at day 0, we expect in successive days 2, 4, 8, 16, and so on individuals in the population, right? So this is a histogram of that population. So more mathematically, if you're starting with a population of P0, which is 1 individual, right? After 1 day, you have 2 times P0, right? Because that P0 divided in 2. And then after 2 days have passed, you have 2P1, which is 4P0 or 2 to the power 2P0. So now I'm asking you, after T days have passed, okay, what is the population P of T? Okay, just do a recurrence formula, right? So you have P1 is 2P0, P2 is 2 squared P0, P3 is 2 cubed P0, and so on. After T days, how many paramecia do you have? How many individuals do you have in the population? Okay. All right. It's 2 to the power T P0. Okay. If you can't see that, just do a couple more. So P3 is 2 to the power 3 P0, and then by recurrence, PT after T days, PT is 2 to the power T P0. Yeah, simple, right? Okay. So now in general, the rate of growth could be any number R. So you don't have to take singular organisms. Take lobsters, for example. 2 lobsters, they meet, they get married, they start making babies. Some of them have 7 babies. Some of them have, 3 babies. Some of them have 17. I don't know how many, how many babies they have, but it could be any number, R, right? It doesn't have to be 2, right? So some pairs of lobsters have 7, some pairs of lobsters have, 1. And so on average could be like 1.5 lobsters every day, right? Or 0.1 lobsters every second, right? So we can make this more general, right? It doesn't make sense 0.1 lobsters every second, but it kind of allows you to think about populations continuously, right? So in general, any population could reproduce at a rate capital R, right? And in general, starting with P0, after T days have passed, the number of individuals is R to the power T P0, okay? Just like we had for the paramecium, that R was 2 because each paramecium divides into 2 exactly, right? That R is 2. In general, R could be any number. Now, even better, we can write this R to the power T. We like exponentials. It's easier to work with exponentials than powers like this. So we write this as P naught e to the power RT, where R, lowercase r, is now equal to log R. Okay, so from now on, think of this lowercase r as an intrinsic rate for the population. Think of it as like compound interest or compound division or population growth. It's nothing, there's nothing fancy about this formula. It's just a way to rewrite that other formula to introduce exponentials, because it's easier to differentiate exponentials and so on. Okay, great so far, no mystery, nothing out of the ordinary. Okay, so now when you look at this population, after T days have passed, you got P naught e to the RT, then that tells you, that formula tells you what happens to the population. If R is positive, then that population is going to grow exponentially. Why? Because you have more birth than death, okay? Or they're not being eaten as fast as they're being born, okay? If R equals 0, then equal birth and death, then that population stays stable, right? It stays at P0. If you had 30 lobsters in the tank, 10 were born and 10 died, right? So you still have whatever P0 lobsters in the tank. And then if R is negative, then more death than birth, then the population is going to decay, right? Just from that single formula. Okay. All right. Remember, this is still a motivating example. Nothing mysterious here. We didn't need differential equations and like, why am I doing this? There's a point. Just bear with me. Okay. Now, in practice, populations are bound by available resources. Okay. There's predation. Okay. There is food availability or lack thereof, right? So typically a population grows exponentially, just like we are on the planet, and we're hitting, after a while, we hit an equilibrium with our resources, birth and death and predation, etc. Right? So typically, in reality, a population starts growing exponentially but then reaches a plateau. We call that plateau the carrying capacity of the population. We describe it with the number K. So it looks something like this, okay? Initially, there's exponential growth, but as the population increases, resources decrease, and we reach a balance. Okay. So now here's my question to you. Assume that due to food restrictions, a lobster population with intrinsic growth rate R, so that's e to the RT, cannot grow beyond K individuals. So find a formula that describes that curve.
Well, I can figure it out.
Or can you develop a formula that describes initial exponential growth and then flattens out? Just from the information you have, just similar to the exercise we did, starting with P0 and then it grows, but then there's K resources. Could you do that? And the question really is, could you even develop a formula like this? Could you even know where to start? I mean, the previous example was easy, right? You just, recursively build that population. But once you put this restriction, could you even do it?
Yes. With respect to K.
No derivatives. I want the formula. I want the formula. I want the formula that describes this population. So I want the formula that tells me after T days have passed, given a K, what is the population number? Okay. Well, in the interest of time, this is a difficult problem, right? I mean, it's a kind of a no-brainer. Like, yeah, there's no way you could develop a formula, probably, a few mathematicians on Earth could figure this out just like that. But for all the rest of us, there's like no clear way that we can develop a formula for a population that behaves like this. Okay. Now the answer is this: P0K over P0 plus K minus P0 e to the minus RT. And you're like, huh? Like, where on earth did you get this formula from? Okay. Well, I got it from building a differential equation for that population and solving that differential equation. Okay. So let's see how building the differential equation for the population is easier than actually deriving this formula straight on. Okay. So let's use that other approach, and we're going to now work with the rate of change of the population rather than the population itself, right? Rather than just directly working with P0, P1, P2, etc., PT, we're going to work with dP by dt, the rate of change of that population. Okay. As a warm-up, the first warm-up problem is consider a population of lobsters with an initial size of P0. Assume that the birth and death rates are equal. So that population is not growing and not shrinking. Okay. So what is the differential equation that governs that population? In other words, what is the rate of change of that population with respect to time? 0, right? There's no change in that population. So dP by dt is equal to 0, right? And you can have an intuitive sense now of what dP by dt means. If we're adding lobsters to that population, on the right-hand side, something should be growing. If we're taking out of that population, on the right-hand side, something must be decreasing. If we're not doing anything to that population, the right-hand side should be 0. Indeed. In that case, since the population does not change over time, then dP by dt, the rate of change of the population with respect to time, is exactly equal to 0, which implies that the solution is P of t equal constant. Okay, good. This is a warm-up. All right. So now let's take it up a notch. Now assume that the lobster population changes at the rate R, so that R times P new lobsters are born per unit time. Why R times P? Because if you had, let's say, lobsters on average, make 1.1 babies per unit time, okay? If you had 2 lobsters, right? So you're going to make 1.1 babies. If you had 4 lobsters, you're going to make 2.2. If you had 6 lobsters, you're going to make 3.3, right? So that's why we multiply R, that intrinsic population growth, by P, by the current population. the more, so you see how the exponential growth is going to show up here. Initially, you start with 2 lobsters, and then you go up to 5, and then with 5, you go up to 12, and right? So you grow exponentially. So now develop you know the rate of change of the population. R times P, new lobsters are born every instant of time. So what is the differential equation, or what is the rate of change, dP by dt in this case? R times P. Okay, think about it. Ethan is saying that the rate of change, dP by dt of that population, is exactly equal R times P. We kind of set that up as a given, right? Indeed, the rate of change of the population will be equal to the change in the population itself, which is R times P. And therefore, dP by dt equal R times P. Now, if you solve that, what do you get? P naught E to the RT, which is what we obtained by doing a bunch of recurrence formulas, right? We had to do a few, P1 equal to P0, and then P2 equal 2 squared, and so on, or R to the power T, etc., right? Whereas all you need to know here is that, well, if the population is changing at the rate R, then dP by dt is Rp, the solution of which is that formula that we developed before. Okay. Now that we did some warm up, here's the big question. What if the population cannot sustain more than a certain percentage of a given population carrying capacity K? So in other words, now I want you to follow the same strategy, dP by dt equals something. But that something now has to stop when the population reaches K. And here's a tip. You want some kind of a switch on the right-hand side that is initially exponential, and then when P hits K, goes to 0, right? Because up there, dP by dt is 0, right? So you want the ODE to behave such that as P approaches K, that right-hand side approaches 0, right? And here's a tip. So R, you have R times P on the right-hand side, right? So now you want R to be dependent on a switch, right? And this is the switch, R times something minus P. What is that something? Okay, some of you are saying K, right? Why? Because when P is equal to K, right-hand side is 0, indeed. Okay, so here's what we do. This is our standard population growth equation, okay? Then if we substitute R by R times K minus P, okay, as our switch, what happens when P is very small initially, K dominates, right? And you have just a constant multiplying P, right? And the population is going to grow exponentially. But as the population approaches K, this number becomes closer and closer to 0 and turns off the differential equation. And then this is what you get. dP by dt R times K minus P times P, okay? Now that switch, when you add that switch and you solve this ODE, this is the answer. And we already went through the exercise. Initially, when the population is small compared to K, P in the parentheses is smaller than K. So K dominates. So you have a constant times P, you have exponential growth initially. But as P approaches K, K minus P gets closer to 0 and takes out that entire right-hand side. So continuously, you are growing that population and then making it reach a plateau. And when you solve that ODE, you get that formula, which is exactly that plot that I showed you. So if you take a moment and think about what we did here, in my opinion, and I hope over time, you'll realize that building that ODE was kind of easier, was less hard, let's say, than building that formula. Because with the ODE, we could reason, okay, it's dP by dt, we know at least the left-hand side. The right-hand side, we know it's some growth rate times P, but we want that growth rate to switch off when it reaches P. That's the only reasoning you had to think about. You could come up with another model. You could say, oh, this is K minus P squared. Still works, right? It's a different way of thinking about it. But see the potential you could have with building those ODEs and just finding solutions for them. Whereas if you went after the population itself to develop this formula, you'd still be working on scratch papers, right? To figure out that formula. So the way I like to think about it, an ODE is a function that is a formula generating function, whereas a formula is a number generating function. So if you take the formula, plug in some numbers in it, it's going to give you a number. If you take, or the solution to a formula, the solution to this, you plug in some numbers, it's a number. The solution to an ODE is a formula, which you subsequently use to get numbers and do predictions. So we took our knowledge now with ODEs one level higher. We can now, or hopefully as you study ODEs, you can develop formula generating tools. That's what an ODE does for you. It abstracts that to a much higher level. Okay, there's actually something even higher level that generates ODEs called calculus of variations. If you study calculus of variations, you have tools that generate ODEs, which subsequently generate formulas, which subsequently generate numbers. Okay. So here's my argument. It's generally easier to relate rates of change of quantities than it is to directly develop algebraic formulas for those quantities. The solution of a differential equation is a formula, where the solution of a formula is just a number. Okay, see the power of the ODE. And the formula that results from the solution of a differential equation usually serves as that algebraic relation that people can use to make predictions to get those numbers. Okay, so again, I'm trying to motivate you for why do we study ODEs in the first place? Okay, why do we study? You'll not hear this in a math course. Okay, you'll not hear this in a, you're hearing theorems and lemmas. No, this is, I want you to have a sense, a feel of how powerful ordinary differential equations can be in your life and in your career and in science and engineering and everything we do. Okay, they're very powerful. Okay, so now that you're a little familiar with rates of change, so I want you to think of a few examples from daily life where you have a rate of change of something going on. And if you've thought about actually like doing some formula for, like, let's say electricity consumption at your home, for example, right? There's a rate of change, right? Rate of electricity consumption over time. And you can plot that. I'm tracking now the rate of radon in our house, and it's kind of oscillating like this, right? And it's subject to pressure changes and temperature. So what other rates of change can you think about daily life? Yeah. The rate of change of fuel consumption as you press on the gas, you stop in traffic, right?
Rate of change until I graduate.
Okay. McKenna? Carbon monoxide concentration in a car. Everything, rate of change, anywhere, everywhere. Yeah, exposure. Yeah, you're driving in a car, right? Or emissions, and like, yeah, in traffic or driving on the freeway, right? Rate of change of your retirement account once you get a job, right? And then you see the stock market going down, like, okay. So everything, it's everywhere. Frankly, you could, even if you couldn't do it, think from now on, say, okay, how about thinking about the rate of change of my electricity consumption or my gas consumption, right? Rather than thinking about the gas consumption itself. Right? And then you start thinking about the factor that influence your rate of consumption, right? Because that's more important than the total consumption itself, right? Okay, whatever affects that rate of consumption. Okay, so I hope I motivated you enough for the study of ODEs. Okay, that's just it, just a motivating example, okay, to get you excited why we study, why they're important. Next, we're gonna dig into the math. Okay, and we're going to start by classifying differential equations in general. Okay, ordinary and extraordinary. All right, so differential equations can be divided into two categories: ordinary and partial. Okay, so they're called ordinary not because the other is extraordinary. They're called ordinary because we only have ordinary derivatives. Okay, we don't have partial derivatives. Okay. So in other words, an ordinary differential equation is a differential equation where you only have a single independent variable. Okay, so you have either t or x at the bottom, or y or z, just one independent variable, time or one dimension in space or something else. Okay, so when you look at it, to identify it's an ODE, you look for the independent variables and you look at the symbol of the derivative. If it's an ordinary derivative, or if you have only a single independent variable, then you better write an ordinary derivative, okay? Because you're differentiating only with respect to one dependent variable. These are some examples of ODEs that we will be dealing with. The first one is the population growth with a carrying capacity K. The second one is one of your homework problems, rate of change of the height of water in a tank as water is coming in and water is leaving through an orifice of area A. Okay, so the rate of change of the height of the tank is going to go up. Is it going to go down? How fast is it going to go down? Right. This is an advection diffusion equation. We will learn that this term is called advection and this term is called diffusion. We'll see an example in a minute. Okay, and change of concentration with some generic right-hand side R. And on the flip side, you have partial differential equations where you have partial derivatives. Or in other words, you have two or more independent variables. Typically, those could be XYZ space or XY space or XZ space or time and space or time and XY and Z space dimensions. So for example, this is the steady state heat equation in 2 dimensions, XY space. This is the unsteady heat equation. Temperature is changing with respect to time and only one space dimension X. The one-dimensional in space, one-dimensional in time, PDE describing the unsteady advection diffusion equation. So this is the counterpart of this one. Okay, you see with this one, we have this additional term which makes it unsteady. When you take out this term, when it's steady state, you only have X as an independent variable, so it becomes an ODE. Okay, so they're two sides of the same coin. In this lecture, in this chapter, we are only going to focus on ordinary differential equations, okay, which also can be classified into several subcategories. Okay, we classify ordinary differential equations into initial value problems and boundary value problems, or in other words, propagation problems and equilibrium problems. So propagation problems mean, initial value problems mean that you are given the state of a system at some initial condition. Okay, this could be a reactor. You put some reactants in a solution and go, tell it go, right? And see how it changes over time. You put a bunch of lobsters together and tell them go. You got the initial condition, right? And they start growing and, you know, populating, etc. Okay, so a well-mixed reactor system is an example of an initial value problem. Filling, emptying a tank is an example of an initial value problem. Population growth, pandemic, disease spread are all examples of initial value problems. Think about initial value problems as whenever you have time in an ordinary differential equation and you have time, you immediately have an initial value problem. You have an initial condition, you're starting from somewhere and you're changing things over time. We're still in ODEs now, okay? We're not dealing with PDEs, we are in ODEs. So initial value problems, ODEs, you have time, okay? For boundary value problems, you are given the state of the system at a physical boundary. So when you think about the heat transfer problem we did earlier, we had fixed the temperatures at the boundary, right? And asked the question, what happens to the temperature in between as the heat is transferred? Contrast that to the initial value problem. We didn't specify anything at the boundary. We said, initially, this is the height of the water, go. Initially, this is the population, go, right? For the boundary value problems, the initial condition doesn't matter, right? Yes. Yes, exactly like the heat transfer problem, okay? This is one example for the heat transfer problem is you have a wall, the outside temperature, 10 Fahrenheit, inside at 70. You have sheetrock, insulation, plywood, and then your siding, right? So heat is being transferred between, you know, it's trying to leak into the outside, but then the insulation is trying to prevent it from leaking into the outside. That's a boundary value problem. What specifies a unique solution here is those two temperatures. only those two temperatures. Clearly, given a heat transfer rate, right? If you fix that heat transfer rate, to change the solution, you change the temperature. So the two boundary values, okay? Okay. So some examples, steady state temperature distribution, curvature of constrained beams, for example, or like those power lines that you see, they settle into, there's a equilibrium for the tension in those power lines. You can solve a differential equation for those. That's how they're designed, how much tension they need to know at the ends of that power line, spring mass systems, and so on, okay? So initial value problems require, these are the laws here, okay? This is a law-giving slide. They require initial conditions. Boundary value problems require boundary conditions. Another tip is when you see time, immediately think this is an initial value problem. When you see space, this is a boundary value problem. In partial differential equations, you have time and space. So it's called an initial boundary value problem. So you combine the two together, okay? All right. Now, furthermore, in the classification of ordinary differential equations, a first-order ODE contains only the first derivative of the dependent variable. And we could have a single equation. And again, we're using the nomenclature phi for a dummy dependent variable. This could be temperature, pressure, height of water, okay? Don't get stuck on phi. Phi is just a placeholder for the name of the variable that, the quantity that you're trying to solve for. And notice how we write ODEs as d phi by dt equals some right-hand side of time and phi. So the right-hand side could be a function of phi itself and could be a function of time. It still is an ODE, okay? It still is an ODE, right? In ODE in space, first-order ODE, this is another first-order ODE in space, where now you have x. So this would be a boundary value problem, for example, and it has x and phi as the dependency on the right-hand side. Or you could have a system of equations. So this doesn't exclude systems of ODEs. If you had two or more ordinary differential equations that are all first order, you can, and they depend on each other, as we will see when we solve the pandemic problem. They're all going to be dependent on each other. Okay, so we can combine them and solve a system of ordinary differential equations. Now notice the change in nomenclature. Now phi is a vector. Okay, phi is a vector of all of the dependent variables. Phi1, Phi2, Phi3, all the way to whatever, however many dependent variables you have. Those could be position, velocity, acceleration, for example, you know, the number of infected people, number of susceptible people, number of recovered people, okay? They all depend on each other. But also notice the right-hand side might depend on all the other ones. So Phi1, the ODE for Phi1 might depend on all the other phis. That's why they have to be solved together. We say that they are coupled to each other. Okay? A second-order ODE contains second and possibly first derivatives of a dependent variable. The advection diffusion equation is a classic second-order boundary value ODE. Okay? This, once you see space, x, you should recognize that this is a boundary value problem. Now, this first term describes diffusion, and diffusion is communication of information at the molecular level. So molecules are vibrating at the molecular level, and they, they're excited, right? Then the molecule next to it gets excited too, and they pass on that excitement throughout. So if you heat one end of the rod, those molecules at the end, they're gonna get like super hyper active, and then they're gonna push that excitement all the way through the rod, right, to the other molecules. So that's diffusion. And it's always associated with the second derivative. Okay, once you take heat transfer and mass transfer, you will learn Fick's law and Fourier's law of diffusion, right? It's always a second derivative, okay? That is describing that process of communicating information at the molecular level. The second term in this equation is called advection. Again, I'm not teaching you about advection and diffusion here. You're gonna learn those in your subsequent courses, but you will be happy when you hit mass transfer, like, oh yeah, I know these, I know what those terms mean. Advection happens completely at the macroscopic level. and it always needs a fluid to transport information along. Okay. So your mom bakes a delicious pie and puts a fan in front of it, and you smell that pie. You know, you're like down in the basement or you're like upstairs, right? And that smell of the pie is so delicious, right? What brought that smell to you? It's the wind blowing through the fan. It transported that food smell, the concentration of those smell molecules, right? It transported them by the air, right? It moved them much faster than they would have moved if you let them just diffuse naturally. So put a drop of ink in water, right, in clear water. If you don't stir it, you'll see it kind of slowly diffusing and moving around, right? Then you go and stir it, and it mixes almost instantly, right? Because you're creating motion of the fluid, and that fluid, the velocity of the fluid is going to transport that information, that concentration around, okay? So this is described by a classic advection diffusion equation. It's one of the most popular equations that you will deal with as a chemical engineer, okay? Advection diffusion, right? So this is a classic example from Mickey Mouse, like, oh, you know, that smell gets, if you have an apple pie over here, you have a fan blowing, and you're looking at the food concentration of the smell of the pie, right? So this is what it looks like. Almost instantly, you can transport that food smell with advection, okay? All right, so let's look at some examples of systems of ODEs, okay? One way to get a system of ODEs is through what we call order reduction, okay? In numerical methods, it is customary, it's always the case that we convert high order initial value problems, so second order, third order, fourth order initial value problems, so those are problems that require only initial conditions, we convert them into a system of first order ODEs. Why? Because it's just easier to say, hey, we're only solving first order ODEs. If you can convert everything to first order, go ahead and do it. Give us your equations and we'll solve it for you. Okay. So here's an example. Take that skydiver. We worked the skydiver example we worked with early on when doing nonlinear solvers, I think. I'm not sure if we did that actually. Maybe that was last year. Anyway, a skydiver jumps from an airplane at t equals 0 and x equals 0. That's kind of the initial distance from the plane. That's where we're measuring distance from the plane, and starts falling to earth. Find the diver's position and speed as a function of time. So you apply Newton's law, okay? In this case, you have d2x by dt squared. Sorry, there's a little typo over here. Let me fix it. Fix it real quick. Okay. So that's Newton's laws. The forces acting on the skydiver, gravity, right? And drag. And in this case, the drag, it depends on the speed, which is dx by dt squared. Okay. And you're given, and this is an initial value problem. Okay. Second order initial value problem, because you have a second derivative here and you have time as an initial value, and you're given these initial conditions, the initial location of the diver and the initial speed of the diver. So the diver is jumping from rest, okay? Now you can reduce this differential equation into two. This is a second order ODE. You can reduce it into two first order ODEs by saying, oh, I'm gonna call dx by dt v for speed. And then if I take dx by dt and substitute it here, I get dv by dt equal g minus alpha v squared. Oh, look, you have two coupled first order ODEs. This ODE depends on v, then the ODE on v, okay, also depends on v, right? So you can solve this and then put in this, solve for x, and so on and so forth. Okay, so you converted a second order initial value problem into two first order initial value problems, okay? And you need that if you're using standard packages like Python and MATLAB. It's also simpler to deal with first order ODEs as once we hit numerical methods for ODEs, okay? Once we hit, once we hit the slides on how we discretize these, okay? It is numerical methods. Thank you for reminding me, Miles. But this is an example of how you get a system of ODEs, okay? Another example, which I'm really excited about, I hope we get to that in time, is a pandemic model. Okay, this is the simplest model for a pandemic was developed like in the 50s. It's called the SIR model or the SIR model, and stands for susceptible, infected, and recovered. Okay, and the idea is you have an initial susceptible population shown here in blue that is being infected at some rate beta. Okay, and as infections start going up, the number of infected people consumes the number of susceptible people, right? And then subsequently, the infected become recovered in green until everyone is recovered. And when we talk about flattening the curve, we want to flatten this red curve so that this maximum does not go over the bed capacity in our hospitals. So if you want a rational way of deciding like how much social distancing and whatever we need, that's what you care about, that maximum of this red curve. And you can relate that to how many number of people are infected. So typically, hospitals and ERs plan for about 30% of the local population to be like maximum infected, like for the flu season, for example, et cetera. So, or 15%, let's say, right? So then how can you work with this model, okay, to see the number of infected? We will derive this together, okay, but this is another example of a system of ordinary differential equations. The rate of change of the susceptible, S, the rate of change of the infected, I, and the rate of change of the recovered. Okay? Yes? No, they are coupled. They're not independent, right? Because, good question. So they are, so we call it a system, because, and that means that they depend on each other, right? If they were independent, they're not a system anymore. They could be solved separately. But this is a system of ODEs, or a system of coupled ODEs. Notice the equation for S depends on I and S, right? Depends on I. So you need an equation for I. Now the equation on I, for I, depends on S as well. So they're coupled. And then the equation on R, for R, depends on I. Okay? So hopefully it won't be a nightmare in this course, okay? All right. So now, why use numerical methods to solve ordinary differential equations? Because we can't really find analytical solutions for all these problems. These problems get complicated very, very quickly. And only for a handful of problems do we have analytical solutions. Now, the analytical solutions are useful to verify and validate our numerical methods, right? So we're not going to dismiss analytical solutions. But for most practical purposes, jumping on a numerical method to solve your system of ODEs or your ODE is one of the first lines of attack you could use when doing research or solving a problem, okay? So, yeah. So hence, there's an immediate need to study how we can solve differential equations numerically. All right. So recap, we'll take a short break. Recap. We looked at the motivation for studying differential equations. It's easier to relate rates of change. It is often easier to relate rates of change to each other than to actually develop a formula for a system. Okay. The solution to a ODE is the formula you're after, right? So an ODE is a formula generating tool, right? It's a formula generating tool. We classified differential equations into ordinary and partial. They're called ordinary because they have ordinary derivatives, and partial, they have partial derivatives, okay? Within ODEs, you have initial value and boundary value problems. Initial value problems, you only need an initial condition. You set that initial condition, go. Okay, population growth, reaction system in a well-mixed tank. Boundary value problems, they need information at the boundary. Heat transfer problem, advection diffusion problems, where things are moving to try to reach an equilibrium between two ends, okay? That's a boundary value problem. ODEs can be first order, second, third, or fourth order, etc. First order ODEs have the highest derivative is first order. Second order ODEs, the highest derivative is second order. You could have a first order and a second order ODE. In a third order ODE, you could have a second and first order as well, but it's still third order. Typically, for high order initial value problems, we reduce that high order ODE into a system of first order ODEs. That's how you get systems of ODEs. That's one way you get systems of ODEs. Other ways to get systems of ODEs is when you have multiple dependent variables that depend on each other, such as the pandemic problem, okay, infected, susceptible, etc. All right, we are back on track, and right now we are gonna focus on initial value problems, okay, and how to solve them. All our initial value problems are going to be described in the form first derivative on the left-hand side equals to some right-hand side. This could contain phi squared, sine t, sine phi, whatever. It's just an arbitrary right-hand side. Given an initial condition at time 0, call it phi 0. Okay. So we're going to start with an example. Who likes lobsters? All right. The best. Yeah. Okay, so that's why I have a footnote here. If you are a vegetarian or don't like lobsters, everything in this example substituted with an eggplant or substitute with a vegetable of your choice, like zucchini. You know, we're not talking about reproduction now. We're talking about cooking them, right? Okay, cooking them. So lobsters, the first time I had a lobster was like a few years after I came to the US, like first ever in my life. I was in Tennessee. No, there's only camels. We probably ate all of them. So anyway. And then we picked like that lobster from, it was a happy lobster, and then it was cooked. It was delicious. I mean, because crabs are popular on the Mediterranean, so they share similar, the meat is very similar. There's actually this article I read. So I keep this lobster example as a legacy example for the way this course was taught in the past. It's an inside joke in the department, but and keeps giving. It's the example that keeps giving. But there was an article I read a few years ago in Seattle. There's this lobster shop. And, like these lobsters, like you see these videos on YouTube, they're like, if you put a lobster like in front of you, it's very creepy, right? And then they walk to the frying pan or something, and it's like really brutal for the lobster. So she started giving them relaxants so that they don't feel that they are being cooked. It's a real thing, a shop in Seattle. Anyway, so here's the made up story over here. A recent report found that the population of lobsters is growing out of hand, okay, beyond control, and those lobsters are eating everything at the ocean floor and destroying the global ecosystem. So the WHO and the CDC is all made up, okay? The WHO and the CDC are recommending that people start eating lobsters as snacks, like, you just get a bag of lobsters, you just chew on them. And as a food engineer, you are tasked for a food company, you are tasked with finding the quickest way for the company to cook those lobsters. And you have two choices. You could either boil them in a liquid, could be like water or oil, or perhaps, air frying them, or baking them in an oven. Okay, and they want their number one optimization is they want to get to cook those lobsters the fastest, the minimum amount of time, reach a well done temperature, I don't know, like 168 Fahrenheit, right? Internal temperature. And you have two options: boiling them in a liquid, water or oil, or baking it in the oven. Okay. So these are some pictures. On the left is a baked lobster. On the right is the lobster being slowly boiled. And then we're gonna convert this now into an ordinary differential equation. Okay. Now you don't. I'm gonna give you this equation. Okay. You're gonna learn how to derive this equation in your heat transfer class, okay? But my interest now here is to just get you to a point where you can solve ordinary differential equations in Python, okay? So you can drive, okay? We're gonna make some assumptions that the lobster is a cylinder of length L. Hey, it's better than assuming the chicken is a sphere, but it's a reasonable assumption, a spherical cat, right? Look at that. I mean, if you ask the lobster to fall, if you tie its hands like its claws like this, right? It looks like a decent cylinder, right? you know, length, let's say 30 centimeters and a radius of 10 centimeters, okay? Then we're going to assume that the lobster remains at a uniform temperature. Okay, now why is this important? If the temperature is changing from one spot on the lobster to another, like the head to the middle to the tail, then we don't only have a change of temperature in time, we only have a change in temperature in space along the lobster. We don't want that because then we will have a PDE, right? I want an ODE. So we're going to assume the temperature is uniform across all of this cylinder. So we only have a change of temperature in time, okay? Very reasonable assumption. The lobster's mass remains constant with time, also reasonable. And the heat capacity, whatever that means to you right now, of the lobster is approximately that of water. So how much heat can the lobster retain before you know, it starts giving away heat, right? So that heat capacity, because the lobster is probably 70% water or something, then we're going to take the heat capacity of water as our heat capacity, okay? These are just numbers that are needed in the equations. We're going to punch in these numbers in Python because we're going to need them for the differential equation, okay? Now, here are the equations for boiling it in water or in a liquid. We also saw this, something similar to this example earlier. It's called convective heat transfer. You have a change of temperature in time that is proportional. There's something here, coefficient, times the current temperature of the lobster minus T infinity. T infinity is the temperature of the fluid. Okay, so you boil the water, reaches 100 Celsius, right? Once the lobster reaches that temperature, there's your switch. It doesn't change in temperature anymore. So once T is T infinity, this becomes 0, similar to that switch in the population, right? So it reaches a steady state temperature, there is no more change. Now H, A, and M, and C, P are, H is the heat transfer coefficient. Okay, for air, it's a lower heat transfer coefficient than water, than oil. Oil has a higher heat transfer coefficient, transfers heat more effectively. That's why, you know, you cook fries in oil, and because it's also more delicious, and you get that cholesterol, delicious cholesterol. So A is the area of the total surface area of the cylinder. M is the mass of the lobster, and this is the heat capacity. Okay, so this is the equation for boiling it in a liquid, right? And the equation for baking it in the oven, it's a kind of radiated heat transfer. Again, you have a rate of change of temperature, some coefficient, but now you have this switch, but to the power 4. Okay, so you have T to the 4 minus T infinity to the 4. T infinity, in this case, is the temperature of the oven, right? So you set your oven bake temperature to 350 or 400, right? That's the temperature, that surrounding temperature. Sigma and epsilon are radiative properties that are given to you as constants. A is the surface area of the lobster, M and Cp are the same, mass and heat capacity, okay? So I'm doing this now to get you to actually solve an ODE in Python, and then we'll look under the hood what's going on, right? So now the question is, we want to solve this. We want to solve these two problems and figure out which one is going to be a faster way of cooking. What's interesting, so we have a few parameters we can play with. We have H over here, which is the heat transfer coefficient. You can choose air, you can choose water, you can choose oil, or you might say, hey, I'm gonna design a new liquid, okay, that has a very high H value so that I can cook the lobster very quickly and much faster, right? You can change your T infinity by also changing the liquid, right? Over here, you only have control over this T infinity, the temperature, the baking temperature inside the oven. Okay, so we want to solve these two equations and compare. Now plot the temperature versus time. Okay, and we're going to see which one is going to reach our desired temperature, 100, whatever, 85 Fahrenheit, 65 Fahrenheit, sooner. Once we solve it, that's really what we're interested in, right? Okay, so our general strategy to solve a differential equation is going to be as follows, okay? So if you're starting with an initial condition for an initial value problem, you're given the ODE, you're given an initial condition, and you're going from some initial time to some Tn. Our objective is to find this red curve, right? But we don't know that red curve. We only know that value over here, and we also know the slope of the curve at every point, right? Because that's the ODE, right? So what we're gonna do, we're gonna divide that time interval from T0 to Tn, we're going to divide it into smaller intervals like we did with the heat transfer problem. But now we're doing it in time. Okay, we're doing it in time, right? And we can assume that the spacing between the 2 points is fixed, some time step delta t, we call that. Okay. Then we're going to develop a formula that allows us a recurrence formula starting with phi 0. We're going to use the information from the ODE to get to the point to estimate phi at time t1. And then we're going to use that to estimate the next point and so on. Okay. So we're going to rebuild that vector. All right. So that's the general strategy. We're not going to talk about how we're going to do that right now. Right now, we're going to talk about how we do it with Python. Okay. We need a win. Now we've been like, oh my gosh, it's stressful looking at these equations. We need a result. We need a win. So let's solve it with Python. Look at some plots, enjoy it, have fun. And then we dig under the hood. So we're going to start with Python. Python, through SciPy, provides a library called odeint. So you can get that from scipy.integrate, provides a library for solving ODEs called odeint. And that means ODE integrate, okay? Not ODE integer, ODE integrate, right? odeint, by definition, this is what the Python folks want it to be like. It solves an ODE of the form, always odeint solves an ODE of the form dphi by dt for right-hand side. Pay attention here, phi t. The first argument on the right-hand side is always phi, and the second argument is always time. Whether your ODE right-hand side has time in it or not, you always write your right-hand side routine as phi and t, the first 2 arguments. That's what odeint wants, not me. That's what odeint wants. Okay, so that they make it general. Then odeint looks like this. At a minimum, it takes 3 arguments. The first argument is the right-hand side of your ordinary differential equation, your initial value problem. This is nothing more than a Python routine that implements the right-hand side of the governing ODE. What is a Python routine that implements the right-hand side of ODE? It's just a Python routine. Def right-hand side, we find right-hand side. Phi t, that's how you write. You don't care what goes in here. Automatically, this is going to be phi and this is going to be t. First argument is phi, second argument is t. And then you implement your right-hand side. Okay, we'll see. We'll do that together. The second argument for odeint is your initial condition. So in the case of the lobster, that's going to be the initial temperature. Okay. The third argument, t, is an array of time points at which you want to solve the ODE. Remember that line where I divided it into some intervals? You could divide it to 100 intervals. You could divide it to 200, right? That's what you provide here. You provide the list or the sequence of points at which you want to estimate the ODE, at which you want to solve the ODE, okay? And ODE returns an array that contains the solution of the dependent variable, in the lobster case, the temperature, at T0, at T1, at T2, all the way to Tn. So it solves the ODE for you numerically, okay, at each one of those points. Let's get our Jupyter notebooks up and running, and maybe we can get this done before time ends. Okay, go ahead and create a new notebook. Okay, so I'm gonna have to turn over here, and those on Zoom, give me a minute so I can move the window over there. Okay. Those in the back, let's zoom in a little bit. All right, so I'm gonna import the boilerplate stuff. You can get it from, let's see, cooking a lobster. Okay. So we're going to import boilerplate stuff, NumPy, Matplotlib, okay, at a minimum. And from scipy.integrate, import odeint. Go ahead, import this stuff, execute the cell. Okay. So let's say our T end, I mean, we really don't know what T end is, right? So we're going to be cooking the lobster. We're going to try to figure out what our time is when we reach 164 Fahrenheit, let's say, okay? So let's allow it to cook for an hour, for example. Let's just solve for the ODE for 1 hour, okay? So our ODE, our T end is going to be, so T0 is 0, and T end is going to be, let's say, 60 minutes times 60 seconds, okay? Because the time in the ODE is standard units, is seconds, right? So now I'm getting T end in seconds, okay? For 1 hour, okay? In seconds, all right? Next, create the array of time points at which we want to solve the ODE. So we're going to see time is equal mp.linspace from 0 to Tn, okay? By default, it puts 50 points. Let's say we put 100 points, okay? Initial condition is equal, initial condition. So that's the initial temperature of the lobster. So you've done cooking before. It's a good practice to take your poultry, your meat out, let it settle to room temperature, right? And then put it on the grill or in the oven, okay? One of the best things you can do in life is cooking. It's a lost art, unfortunately. You should spend an hour a day cooking. Okay, so let's say 311 room temperature. This is in Kelvin, okay? Room temperature. Initial temperature of lobster. The lobster.
Damn, what is that?
It's a little warm. It's a Mediterranean room. But that's a good question, Maz, because this is going to be a factor that influences like how fast you're cooking. What should be stored in the freezer, should put in the fridge, you know. So this would be a variable in your solution process. Okay. Sure, and we can try that too. Maybe we put it at, I don't know, 200. We can play with those numbers, all right? So now, excuse me, okay. So ODEint, if you call ODEint, it's gonna require a right-hand side function, that first argument. So we need now to build the right-hand sides for both problems, advection, the boiling it in water, and baking it in the oven. You have two equations, right? So we're gonna create those two right-hand sides. So we're going to define RHS boiling, okay? And by definition, boiling brings the right-hand side routine for ODEint always takes two arguments. The first argument is phi, the dependent variable, and the second argument is time. So in this case, I'm going to call it t and time, lowercase t and time, okay? All right, so for boiling, let me grab the slides. All right. Okay, so for boiling, we had minus HA over MCP, T minus T infinity, and we have all of this information over here, okay? So let's go ahead and implement all of those numbers. So we have length L is 0.3. So over here in this right-hand side boiling, I'm literally gonna program this HA over MCP times T minus T infinity, okay? So let's say L is 0.3 meters, okay? And then R is the radius is 0.1 meter. A is 2.0 times pi, so that's the surface area of the times of the cylinder, 2 pi RL plus 2 times pi times R squared. So those are the ends, right? And mass is 1 kilogram. And heat capacity for water is 4,200 decimal points. And finally, so this is equal. Finally, result is equal, that's my right-hand side, minus h times a. Oh, we didn't define h. So let's define h. Let's say equal, this is equal to 1 or 10. We're going to play with that number. Okay, HA over MCP times T minus T infinity. We didn't define T infinity either. So let's say T infinity. What do you want to put T infinity as for, let's say for water, let's say 350, okay? Now you see this right-hand side doesn't have time in it, but that's okay. You have to put time as an argument because that's what ODE requires. But we never use time in it. But we use P, right? P, that's our dependent variable. You could have called it phi here, then you have to call it phi here. Okay? That's the right-hand side boiling. Okay? Let's do the right-hand side baking, and then we'll solve it, okay? So I'm going to copy this here. Define right-hand side baking. Again, takes the first argument is phi, the dependent variable. The second argument is the independent variable. Again, now, in this case, for that other right-hand side baking it in the oven, there's no H, there's no heat transfer coefficient. However, there is sigma, which is 5.67.
Professor Saad, I'm not sure if you can hear me, but don't we need to return?
Yes, thank you. Yes, thank you. We have to return result. Thank you very much. Okay, so return result over here. Okay. And for this one, 5.6704, e to the minus 8. Okay. And then emissivity is epsilon, which is 1. Okay. Now T infinity for the oven, let's say it's 400. Okay. L, R, A are the same. And then over here we have minus sigma times epsilon, okay, times A over MCP times T to the power 4 minus T infinity to the power 4. Return results. Whew.
So in the so I remember earlier we were doing one of them with T's and Kelvin, like the room temperature we were doing Kelvin. Yeah, T's are the 3 to 7. Now are these temperatures in Kelvin or are these?
Kelvin. Okay. Yeah. So when you put the oven at 450 Fahrenheit, you know, you can convert that to Kelvin. I'm just putting it just a number over here. Let's say 400 Kelvin. We can play with those numbers. This is the point now, is that we can value those parameters and we see the different curves, how they're changing. Okay. So let's solve it. Okay, so now ODE int, we can call ODE int twice. Once for this ODE and once for the other one. And all we need is the right-hand side for each. And ODE returns a sequence of solutions, right? So we're going to say T boiling in water, or T boiling. So that's the temperature of the lobster when boiling it in water, is ODE int. Which right-hand side should we give it? Right-hand side boiling, right? Because that's the right-hand side for the boiling it in a liquid. We're going to give it an initial condition T0, which we defined way up here, okay? And we're going to give it the sequence of time, which is time, our length space. And T baking is equal ODE int, RHS baking, T0 and time. You run it, it throws an error. Name T0 is not defined. I guess I didn't execute this cell. Okay. All right, great. So who's ready to plot this? I want to plot it. Let's plot it, okay? So plt.plot, okay, we're going to plot those two. So plt.plot, I'm going to plot on the x-axis time, but I'm going to divide it by 60 because I want to look at it in minutes. Okay, not in seconds. I will look at it in minutes. Okay, remember our time was in seconds, and I'm gonna do T boiling for the first one, and we're gonna do flat dash fine, and then for the baking, we're gonna do T baking, and we're gonna do it in red dash dot, and this is what we get. Okay, so I'm gonna have to expand this plot a little bit and maybe zoom out. Okay, all right. So now let's add a grid. Okay, plt dot grid. All right. Okay. So now you see. Okay. So let's say what is 164 164 Fahrenheit to Kelvin. Okay. 164 Fahrenheit is what they call well done. Okay. For fish, and that's about 300 or 350 kelvins. Okay. So once we reach this point, then it's been cooked, right? So this is telling us with the baking it in the oven at these conditions, we can do it in about 15 minutes, right? We can do it in about 15 minutes, okay? So let's add a line for the x h line, y equal 300. So that's the well done temperature, and line style is equal dash dot. Okay, so this horizontal blue line is the well done temperature. Okay, so once the curve hits that line, it means we cooked it. But look at the boiling in that whatever liquid, the heat transfer coefficient of what was sand is taking such a long time, it's taking forever. Okay.
That's not a curiosity.
Accurate. It's not 100% accurate, but it kind of gets in the ballpark. It's reasonable. It's reasonable accuracy, right? It is good for our intents and purposes, right? So we can fine tune it if we take measurements and get some actual properties of the lobster, etc. Right? You can fine tune it and get to. I mean, I would expect a lobster to be cooked in 20 minutes, right?
Yeah, that's
right.
Well,
that's what I'm expecting, right? Yeah.
For this specific situation, I
Yeah.
don't think the lobster can hour the boil.
Well, that fluid. Okay, hold on. Probably the heat transfer coefficient, this one is for air. So this is air frying the lobster. If you want to go for water or for oil, that H, this is what we're going to do right now. So that H for the heat transfer coefficient for oil, for example, is like 500 or 1,000. Okay, so let's put 500 here. And the T infinity for the oil, because oil boils at a much higher temperature, so you can increase T infinity. You can go to 400 here. Okay, so now when you solve it, look what happens. Like this fluid, this weird fluid, gets it in like 1 minute, which is very unusual. So probably that H was very, very high. If you can design a fluid that has such a high H, right, then you can, yeah, fill it up. Now let's go to freezing temperature, like your colleague said, Todd said. So let's go, I don't know, 273. Well, Todd was saying that, right? It barely made a difference with such a high heat transfer coefficient. Now, reasonably, those heat transfer coefficients are on the order maybe of 10 or 100. Then you can put this, look at that, for example. For these conditions, they're almost matching each other. So there's no practice, right? So, but the point is to illustrate the power of this method. We just solved two ODEs, two complex ODEs, right? The radiation one is a nonlinear one, right? There's no easy solution for that. You have all of these parameters that you can change, right? On what is today, Tuesday? On Thursday, we're gonna learn how to pass these parameters to the ODE to the right-hand side, so we don't have to go to the right-hand side every time. So we'll just change them in ODE int, okay? And we'll continue building on it, okay? All right, I hope this was helpful today. Guys on Zoom doing all right? Have any questions?
Can you scroll up a bit?
Up?
Yeah, right there's fine.
This is good. All right.
Yeah.